A 7-mile-wide visitor from another star system just smashed through our solar neighborhood. It is moving at 137,000 miles per hour. It is carrying chemistry that should not exist in nature. 3. I divided by Atlas is rewriting the rules about what roams between the stars. You will discover a comet that breathes carbon dioxide instead of water. It bleeds nickel without any iron and has survived longer than most galaxies. 3. I divided by Atlas appeared on our telescopes like a cosmic missile. It was moving much faster than anything natural should be able to move. At 7 miles across, this interstellar wanderer dwarfs every space visitor. Every space visitor that we have ever encountered before. Think of it in this particular way to understand the scale. If the famous ʻOumuamua was a single grain of rice, 3 I divided by Atlas would be the size of a bowling ball. The size difference between them is so incredibly extreme. Astronomers calculated that we should discover 10 million smaller objects. We should find them before we find one this massive, yet here it sits defying every statistical model that we have built. Models about what is supposed to be traveling between the stars. The speed of this object tells an even more dramatic story. 3 I divided by Atlas races through the vacuum of space at 58 kilometers per second. It carries what scientists call hyperbolic excess velocity. This technical term hides a very violent and dramatic truth. Something catastrophic must have launched this mountain-sized chunk of ice and rock. It must have launched it from its home system with enough force to escape. Not just the gravity of its planets, but the entire gravitational embrace of its star. What kind of cosmic disaster is able to create such a high-velocity picture giant planets that are dancing too close to each other? Their powerful gravitational fields becoming like weapons. Weapons that can hurl smaller objects out into the void of space. Or you can imagine a dying star that is swelling to an enormous size. Its expanding atmosphere would be creating powerful pressure waves. These waves could blast comets out into interstellar darkness. 3. I, divided by Atlas, bears the ancient scars of such a violent event. These scars are frozen into its trajectory for billions of years. The discovery of this object itself reads like science fiction. The Atlas telescopes in Chile are designed to scan the entire sky. They do so multiple times each and every single night. They use artificial intelligence to spot any moving dots against the static background of all the distant stars. On July 1, 2025, the machine learning algorithms flagged something. They flagged a very unusual and fast-moving object. Within a matter of hours, observatories all across the globe, they swung their powerful instruments toward this cosmic intruder. The initial measurements of the object shocked everyone. 3 I divided by Atlas is following what astronomers call a hyperbolic orbit. It has an eccentricity of 6.141. In simple terms, it will approach our Sun just one single time, and then it will never ever return to our solar system. The mathematics of its orbit revealed something even stranger. This visitor is approaching from a very specific direction. A direction that aligns almost perfectly with our solar system's equatorial plane. The probability of such an alignment happening by random chance is very low. It is less than 0.2%. Professional astronomers began whispering about statistical impossibilities. Objects that are this large, moving this fast and arriving from this direction, they should not exist according to our current models. Our models of how comets get ejected from their stellar systems. 3 I divided by Atlas had announced itself as a complete anomaly. An anomaly that would challenge our fundamental assumptions about space. The space that exists between all of the stars in our galaxy. However, the real surprises of this object were only just beginning. They were only just beginning to emerge from the deep darkness of space. 3 I divided by Atlas carries the fingerprint of cosmic violence in its impossible speed. When astronomers measured its 58 kilometers per second of hyperbolic excess velocity, they realized that they were looking at something that had experienced a traumatic ejection, an ejection from its own birth system long, long ago. This high speed represents a great deal of pure kinetic energy, the mathematical signature of an object that has escaped not just planetary gravity, but it has broken free from its parent star entirely. Think of it as being like a bullet that has been fired so hard that it not only leaves the gun, but it also escapes Earth's gravity, and it then flies off into the vastness of space forever. The physics that is behind such a high velocity reveals catastrophic scenarios. Computer simulations have shown that achieving this kind of speed requires something. It requires gravitational encounters with objects that are at least as massive as Jupiter. Picture 3. I divided by Atlas as a smaller body that was orbiting peacefully, orbiting in some distant solar system billions of years ago. Then the massive planets in that system began to migrate inward. Their powerful gravitational fields would have created chaos in the outer regions. The outer regions where all the comets and asteroids reside. During these cosmic billiard games, the smaller objects get flung around. They get flung around just like marbles on a table. Most of them would have crashed into the planets or been ejected at modest speeds. But occasionally, the gravitational mathematics can align perfectly. They can align to create what scientists call a gravitational slingshot effect. The object gets accelerated to a tremendous velocity, enough velocity to be able to break free from its stellar system entirely, and to begin a billion-year journey through the interstellar space. Alternative scenarios for this are able to paint even more dramatic pictures. Imagine 3I divided by Atlas forming around a binary star system, a system where two different suns are orbiting each other. As these stellar companions begin to age over time, one of them might expand into a large red giant star. This would disrupt the delicate gravitational balance of the system. The expanding stellar atmosphere would create powerful pressure waves and radiation. This could blast the smaller objects out into the void with tremendous force. Even more extreme possibilities involve what are known as stellar encounters. Our galaxy contains over 100 billion different stars. All of them are orbiting the galactic center in complex patterns. Occasionally, two of these star systems will pass close enough to each other, close enough for their gravitational fields to be able to interact. During such encounters, the smaller bodies in the outer regions of both systems, they can get ejected at tremendous speeds into interstellar space. They would be launched into the space between the stars like cosmic refugees. The high speed of 3I divided by Atlas also reveals something profound about time and distance. At 58 kilometers per second, this object has been traveling for a long time. It has been traveling through interstellar space for potentially billions of years. It has been able to survive the harsh radiation environment between the stars, where the cosmic rays can strip away the surface materials of an object, and the solar winds from distant stars create a very hostile environment, an environment that is known to destroy smaller objects. Yet 3I divided by Atlas has been able to endure this long journey completely intact. Its internal structure has been preserved like a time capsule from an ancient and distant stellar system. The chemistry that is locked deep inside its nucleus represents the conditions that existed when our galaxy was much younger, when different types of stars were dominating the cosmic landscape and planetary formation was following different rules than we observe today. The mathematics of its trajectory suggests that it originated from somewhere in the galactic thick disk, a population of ancient stars. These stars were formed when the Milky Way was still very young and chaotic. These stellar systems are known to contain lower concentrations of heavy elements, lower than our own Sun, suggesting that 3I divided by Atlas formed under different conditions that were dramatically different from anything in our solar neighborhood. But the real mystery lies in how our artificial intelligence systems managed to catch this cosmic bullet at all in the first place. 3I divided by Atlas should have remained completely invisible to us forever. But our artificial intelligence was able to catch it in an act of cosmic luck. An act of luck that might happen only once in all of human history. The Atlas telescope network operates like a kind of robotic sentinel. It is scanning enormous chunks of the sky multiple times each night. 4 different telescope stations are spread across Hawaii and South Africa. They photograph the very same stellar fields repeatedly, over and over. They are comparing all of their images to detect anything that moves against the fixed background of the distant stars. The system is able to process over 100 gigabytes of data. It does this every single night that it is in operation. It is analyzing millions of individual stellar positions. It is doing this with its powerful machine learning algorithms. Finding 3I divided by Atlas required detecting a tiny dot of light, a dot that moved just enough between the photographs to register as motion, but not so much that it appeared as a streak or a blur. The object's hyperbolic velocity means that it is crossing the sky faster. It is crossing faster than typical asteroids or comets do. This creates a very short detection window for us, a window that is measured in days rather than in months. If you miss that window, the visitor will disappear forever. It will disappear into the darkness that is beyond our solar system. The artificial intelligence systems had to distinguish this one object. They had to distinguish it from thousands of different false positives. False positives that are generated by the system every single night. Cosmic rays that are striking the telescope's sensors can create bright spots. These spots can mimic the appearance of moving objects. Satellites and pieces of space debris can produce streaks. These streaks can confuse the detection algorithms that are being used. Even birds that are flying in front of the telescope lenses can trigger alerts. These alerts can waste a great deal of precious observing time. The machine learning algorithms have been trained on years of sky survey data. They have learned to recognize the subtle patterns that indicate genuine objects, genuine astronomical objects, versus the instrumental artifacts. 3I divided by Atlas appeared as a point source that was moving at a consistent velocity. It moved across multiple different images of the sky. It was following a trajectory that matched the laws of gravitational physics. It was not random noise or some kind of equipment malfunction. The timing of the discovery represents a form of astronomical serendipity. 3I divided by Atlas just happened to pass through regions of the sky. Regions that the Atlas survey was regularly observing. It did so during clear weather conditions that allowed the telescopes to operate. Cloud cover equipment, maintenance, or even routine calibration procedures. Any of these things could have prevented the detection entirely. The object would have sailed right through our solar system completely unnoticed. A cosmic visitor that humanity would have never known existed. Once it was flagged by the machine learning systems, 3I divided by Atlas triggered an international alert network, a network that connects observatories all around the globe. The Minor Planet Center in Cambridge is what coordinates these discoveries. It verifies the initial observations and calculates the preliminary orbits. Within a matter of hours of the Atlas detection, telescopes in multiple different countries were already tracking this intruder. The follow-up observations revealed the true scale of what had been discovered. Ground-based telescopes were able to measure the object's brightness, and they were able to estimate its very large size. Spectroscopic instruments began to analyze the light that was reflected. The light that was reflected from the surface of 3I divided by Atlas. This revealed the chemical composition of its surface materials. Radio telescopes began to search for any signals of artificial origin, while infrared instruments measured the heat emission to determine its structure. The global response to this discovery demonstrates how modern astronomy operates. It operates as a coordinated and international effort. Space agencies, universities, and research institutions all shared their resources. They shared telescope time and data processing resources. They did this to maximize the scientific return from this rare opportunity. Observing schedules were reorganized to prioritize the measurements. The measurements of this one single important object, recognizing that interstellar visitors provide unique windows into the stellar systems that are beyond our own. Computer models began to predict the object's future trajectory. They were calculating the optimal viewing opportunities that would exist before it disappeared forever. The mathematics revealed that 3:1 divided by Atlas would remain visible. It would remain visible to Earth-based telescopes for only a few months. It would then fade beyond our detection limits forever. However, the chemical analysis of this object would soon reveal something. It would reveal signatures that had never been observed in nature before. 3I divided by Atlas is bleeding chemicals that should not exist together, not in any natural object that is known to science. When the first spectroscopic measurements arrived from the major observatories, astronomers found themselves staring at data that was impossible, data that violated all of the basic expectations about comet chemistry. Every single previous comet that has been studied by humanity, it has shown specific ratios of water, carbon monoxide, and carbon dioxide. These ratios reflect the formation conditions in the outer regions of the stellar systems where they formed. 3I divided by Atlas has shattered all of these known patterns completely. The initial chemical fingerprint of this object revealed something. Carbon dioxide emissions were dominating everything else. Typical comets are known to release mostly water vapor. They do this when they are heated by approaching their stars. This creates the familiar bright tails that are visible to amateur astronomers. 3I divided by Atlas instead is spewing out carbon dioxide. It is doing so at ratios that dwarf the water production. It is doing so by factors that should be physically impossible under any of the normal formation scenarios. Spectroscopic analysis works by spreading the light from the object, spreading it into its component colors, and revealing absorption and emission lines. These lines correspond to specific molecules in the object. Each chemical compound is known to absorb and emit light. It does so at very characteristic and specific wavelengths. This creates a unique fingerprint that allows astronomers to identify materials. They can identify materials across interstellar distances. The spectrum of 3:1 divided by Atlas showed lines that corresponded to carbon dioxide. These lines were so intense that they overwhelmed nearly everything else. The chemistry of this object gets even stranger when you examine what is absent, what should be present but appears to be absent or depleted. Water vapor is the most common volatile material in comets throughout our own entire solar system, but it appears in 3:1 divided by Atlas at concentrations that are far below normal. Carbon monoxide is typically abundant in objects that are formed in cold regions, but it shows up in smaller quantities than expected for an interstellar visitor. Even more puzzling are the signatures of its organic chemistry. 3I divided by Atlas shows some evidence of complex carbon chain molecules, but they are in ratios that are different from any comet previously studied. The object also appears to contain some cyanide compounds. This was revealed through characteristic emission lines in the ultraviolet spectrum. These molecules suggest some very specific formation conditions, or they suggest processing mechanisms that remain poorly understood. The chemical anomalies of this object extend beyond simple molecular ratios. They extend to the isotopic compositions of the elements. Different isotopes of the same element are known to form under specific conditions, specific temperature and pressure conditions in space. This creates signatures that can persist for billions of years. 3I divided by Atlas shows isotopic ratios that suggest a different formation. formation in environments with different stellar radiation fields, and different chemical abundances than what we have in our solar neighborhood. Professional chemists and planetary scientists began to propose exotic scenarios to explain these very strange observations. Perhaps 3I, divided by Atlas, formed in a stellar system with unusual metallicity, where the abundance of the heavy elements differed significantly from solar values. Alternative theories suggested that processing by interstellar radiation over billions of years might have altered its surface chemistry. It would have done so through mechanisms that are unknown in our solar system. The strangest possibility involved its formation beyond the traditional ice lines, where different volatile materials are known to freeze out of protoplanetary disks. 3I divided by Atlas might represent materials that condensed in a region where carbon dioxide dominates over water ice. This would require stellar system architectures that are completely different from our own solar system's organization. Laboratory experiments are not able to replicate the conditions that 3I divided by Atlas has experienced during its formation and its subsequent billion-year journey through interstellar space. The object is carrying the chemical signatures of environments and processes, environments that exist nowhere in our local cosmic neighborhood. This makes it a unique laboratory for studying exotic astrophysical chemistry. Yet the carbon dioxide emissions reveal an even more industrial-scale mystery. 3I divided by Atlas is producing carbon dioxide at incredible rates that are able to rival industrial manufacturing plants here on Earth. The James Webb Space Telescope's measurements of this object have revealed something. 3I divided by Atlas is expelling 129 kilograms of carbon dioxide. It is doing this every single second that it is active. To put this number into perspective for you, imagine a factory assembly line that is producing carbon dioxide, producing it continuously at the rate of a small automobile every few seconds. This high production level is creating an invisible cloud of gas, a cloud that is extending over 200,000 meters from the comet's nucleus. The carbon dioxide to water ratio has been measured at 8:1. This represents the most extreme imbalance that has ever been recorded in any comet that we have ever studied before. Typical solar system comets show ratios that are much closer to 1:10, and they show it in the opposite direction, with water dominating. Water is dominating the carbon dioxide by enormous margins. 3I divided by Atlas has inverted this relationship so completely that it challenges our fundamental models of how volatile materials freeze, how they freeze and organize in the protoplanetary disks. Understanding these high emission rates requires examining the physics of how a comet becomes active in the first place. As 3I divided by Atlas approaches our Sun, the solar radiation heats its surface. This causes the frozen materials on its surface to sublimate. They go directly from a solid to a gas without melting. The process is very similar to how dry ice evaporates in warm air, but it is scaled up to geological proportions and sustained for many months as the comet follows its hyperbolic trajectory. The energy balance calculations for this process reveal some puzzling aspects. Carbon dioxide is known to sublimate at higher temperatures than water ice. This means that it should become active later as a comet approaches its star. 3I divided by Atlas is defying this expectation by showing robust carbon dioxide production. It is doing this while its water emissions remain relatively modest. This suggests that it has an unusual surface composition or internal structure. One explanation for this involves a phenomenon called preferential sublimation, surface layers that are enriched in carbon dioxide ice. They can create a barrier that prevents water vapor from escaping. Imagine 3I divided by Atlas as having developed a carbon dioxide-rich shell, a shell that it developed over billions of years of interstellar travel. The water ice would be trapped deeper inside the nucleus. It would be where the solar heating cannot reach it effectively. Alternative theories have proposed that it formed in a different kind of system, a stellar system where carbon dioxide ice was more abundant than water ice. This would be due to different chemical conditions during planet formation. Such systems might exist around stars with different metallicities, or they could have different radiation environments than our Sun. This would create protoplanetary disks with inverted chemical gradients. Inverted compared to our own solar system's organization. The production rates can also reveal information about the internal structure and the porosity of 3-1 divided by Atlas. High gas production requires efficient pathways for the sublimated materials, pathways to escape from the interior regions where the heating is penetrating. Computer models have suggested that the nucleus contains a network of cracks, pores and cavities that allow the gas to percolate. It would percolate through the structure and then reach the surface. Spacecraft missions to solar system comets have revealed complex internal structures. They have distinct layers of different chemical compositions. 3I divided by Atlas might represent an extreme example of such layering. It could have carbon dioxide-dominated regions that are separated from water-rich regions, separated by barriers that prevent any efficient mixing during sublimation. The massive carbon dioxide cloud that is surrounding this object, it is creating both observational opportunities and challenges. Infrared telescopes can be used to map the three-dimensional structure, the structure of this gas cloud, which can reveal information about the wind patterns and the heating mechanisms. These are things that remain invisible light observations. However, the cloud is also obscuring the nucleus itself. This makes any direct measurements of the central object very difficult. But hidden within this carbon dioxide factory lies an even stranger mystery. 3I divided by Atlas is emitting metallic nickel vapor without any trace of iron. This is a chemical signature that has never been observed in nature before. The Very Large Telescope in Chile has detected atomic nickel emission lines. It has detected them in the spectrum of 3-1 divided by Atlas. It used instruments that are sensitive enough to identify individual elements, identify them in the coma of the comet as it outgasses. Nickel appears as characteristic green emission lines in the spectrum. These lines are at specific wavelengths of light. They are created when the nickel atoms get excited by the solar radiation, and they then re-emit the light at frequencies determined by quantum mechanics. The detection of this itself represents remarkable astronomical detective work. The nickel emissions from comets are known to be extremely faint. They require very long exposure times with the world's most sensitive spectrographs. The signal from 3-1 divided by Atlas showed up clearly in multiple independent observations. This has confirmed that this interstellar visitor is releasing significant quantities of metallic nickel vapor as it approaches our Sun. What makes this discovery so extraordinary is the complete absence of iron. The complete absence of iron emissions in the very same spectrum throughout the entire known universe that we can observe. Nickel and iron are always found to appear together. They are in consistent ratios that are determined by nuclear physics. These elements are formed through similar stellar nucleosynthesis reactions, and they get incorporated into planets and smaller bodies in predictable proportions. Finding nickel without any iron violates our fundamental expectations, our expectations about the nature of cosmic chemistry. On our own planet Earth, nickel and iron are always found together. They are found in meteorites, planetary cores, and industrial alloys. This is because they share very similar chemical properties and formation mechanisms. The ratio of nickel to iron in solar system objects reflects the original composition of the stellar nebula from which our planets formed. 3I divided by Atlas is breaking this known pattern so completely. that it suggests formation processes or subsequent processing that remain unknown to science at the present time. The nickel emissions from this object also show unusual time-variable behavior that is defying our conventional understanding of these things. Between July and August of 2025, the intensity of the nickel lines, it increased by a factor of 25 in the spectrum. It was following a steep mathematical progression that suggests systematic changes in the comet's internal structure or surface composition. Laboratory studies of nickel-iron separation require extreme conditions. They require high-temperature industrial processes or exotic chemistry that is not found in any natural environments. Smelting operations and electrochemical processing can separate these elements, but such processes require technological capabilities and energy sources that are unavailable in the space environments. Some researchers have proposed that 3I divided by Atlas might contain nickel-rich minerals that are able to sublimate at different rates than iron-bearing compounds. Under this scenario, the surface heating would preferentially release the nickel. The iron would remain locked in more thermally stable compounds that are deeper within the nucleus of the comet. However, no known mineral phases show such an extreme fractionation. A fractionation between these two chemically similar elements. Alternative explanations for this involve exotic formation conditions in the stellar system where 3-1 divided by Atlas originated, perhaps unusual stellar radiation environments or magnetic field configurations. Perhaps these created chemical separation mechanisms that are unknown in our solar system. The object might represent materials that have been processed by phenomena that exist only in specific types of stellar systems with different physical conditions than our own. The possibility of artificial processing cannot be dismissed entirely, though it does remain a highly speculative idea at this point. Industrial separation of nickel from iron is known to produce waste streams that are enriched in pure nickel, creating signatures that might persist if they are incorporated into larger objects. However, such processing would require technological civilizations, and it would require manufacturing capabilities operating on a large scale, a scale far beyond our current human industrial capacity. The metallic emissions pattern of this object has sparked discussions about its possible artificial origins that would soon reach the public. 3I divided by Atlas has endured longer in the harsh depths of interstellar space. It has endured longer than most of the galaxies in our universe have existed. Computer models that have traced its trajectory backward through time, they suggest that this object has been wandering between the stars, wandering for potentially 7 to 14 billion years. To appreciate this immense timescale, you can consider our own solar system. Our entire solar system formed only 4.6 billion years ago. 3I divided by Atlas might have been ejected from its parent system, ejected when the universe was less than half of its current age. Surviving such long time frames in interstellar space requires withstanding environmental conditions that can destroy smaller objects. They can destroy them within just a few millions of years. Cosmic rays are high-energy particles that are accelerated by supernovas and other violent astrophysical events in our galaxy. They are constantly bombarding the objects that are traveling between the stars. These particles are able to penetrate the surface layers of these objects, and they can create chemical changes that alter their composition and structure. The radiation environment between the stars is very different. It is different from the conditions that are within the stellar systems, where the planets and the comets are able to form. Interstellar space contains a very dilute gas and dust, but it lacks the protective magnetic fields and the stellar winds. These are the things that shield objects in orbit around stars. 3I divided by Atlas has experienced direct exposure to this galactic cosmic radiation. It has done so for many billions of years of its existence, yet somehow it has managed to preserve its internal structure. And it has preserved its chemical composition as well. Research into the cosmic ray processing of small bodies suggests something. Objects that are smaller than several kilometers across can be disrupted, or they can be chemically altered beyond all recognition. This happens during these extended interstellar journeys. 3I divided by Atlas is able to exceed this critical size threshold. It does so by very substantial margins in this case. This has allowed it to survive the bombardment that would destroy smaller wanderers. The surface of this object has likely developed a certain kind of crust, a radiation-processed crust during its billion-year journey. The cosmic ray impacts are known to break the chemical bonds. They break them in the surface materials of the object. This can create new compounds and alter the physical properties. It can alter the properties of the outer layers of the object. This processing might be able to explain some of the unusual chemical signatures, the signatures that have been observed in the spectroscopic measurements, laboratory experiments that use particle accelerators to simulate cosmic ray bombardment. They have shown that organic molecules can be destroyed or transformed. They can be transformed into simpler compounds over time. Timescales that are much shorter than the age of 3I divided by Atlas. Yet this object shows some evidence of complex carbon chemistry. This suggests either its formation with unusual organic compositions, or it suggests some protection mechanisms that have preserved these materials. The internal temperature of 3I divided by Atlas during its journey was very low. It remained close to absolute zero at around -400 degrees Fahrenheit. At these incredibly low temperatures, all chemical reactions proceed slowly. This helps to preserve the original composition of the object, the composition that it had when it formed billions of years ago. The object essentially became a kind of a frozen time capsule, a time capsule that is carrying pristine samples of ancient materials. Gravitational interactions with passing stars might have altered its orbit. They might have altered it multiple times during its interstellar journey. Computer simulations have suggested that objects with such long travel times, they will encounter numerous different stellar systems. They will receive gravitational perturbations that change their trajectories. 3I divided by Atlas has been able to survive all of these encounters. It has survived them without fragmentation or capture by other systems. The thickness of any radiation-processed surface layer can provide clues about the duration of its interstellar travel. Spectroscopic measurements are only able to probe the outermost surface. This means the unusual chemistry that has been observed, it might just represent billions of years of cosmic ray processing, and not the original formation conditions of the object. The deeper layers of the object might be preserving materials with compositions that are more similar to typical solar system objects. However, the origin point of this ancient wanderer reveals even more mysteries. Mysteries about the evolution of our own galaxy. 3I divided by Atlas has originated from the most ancient and violent region of our galaxy. It is carrying the chemical signatures from the cosmic dawn. Astronomers have been able to trace its trajectory backward through space and time. They have used computer simulations that account for the gravitational influence, the influence of billions of stars over millions of years. These calculations are pointing toward the galactic thick disk, a population of ancient stars that were formed when the Milky Way was young. They were formed when it was young and chaotic, approximately 10 billion years ago. The thick disk represents a kind of a fossil record of our galaxy's very violent and chaotic youth. This was a time when star formation was proceeding at rates 10 times higher than what we see in our galaxy today, and massive stellar explosions were enriching the interstellar space. enriching it with the first of the heavy elements. Stars in this particular population show chemical compositions that are dramatically different from our own Sunday. They have lower abundances of the elements that are heavier than hydrogen and helium. 3 I divided by Atlas is carrying these ancient chemical fingerprints. Understanding the galactic structure requires visualizing the Milky Way, visualizing it as consisting of distinct components that were formed at different times. The thin disk is where our own solar system resides. It contains the younger stars that were formed from gas that was already enriched with heavy elements from previous generations. The thick disk is what preserves the stars that were formed much earlier. It was a time when the chemical enrichment was still incomplete, and the star formation was following very different patterns. The chemical analysis of this object has revealed its metallicity, a metallicity that is consistent with the thick disk stellar populations. The term metallicity refers to the abundance of the elements that are heavier than hydrogen and helium. Astronomers call all of these elements metals, objects that have formed around the thick disk stars. They show metal abundances of about 40% of the solar values. This is matching the observations that have been made of 3-1 divided by Atlas. The high velocity of this object also supports a thick disk origin. Objects that are ejected from stellar systems will inherit some of the motion, the orbital motion of their parent stars around the galactic center. The thick disk stars are known to move in highly elliptical orbits. These orbits can carry them far above and below the galactic plane. This creates velocity distributions that are different from the thin disk. 3 I divided by Atlas shows kinematic properties that are consistent with this, consistent with an ejection from a thick disk stellar system. Formation in the thick disk environment would have subjected this object. It would have subjected it to conditions that are absent in our local neighborhood. Higher stellar densities would have increased the frequency of gravitational encounters. These encounters can be what ejects comets and asteroids from planetary systems. More massive stars are known to produce stronger stellar winds, and they produce more intense radiation fields that can alter the chemistry. They can alter the chemistry of the nearby protoplanetary disks. The chemical composition of 3-1 divided by Atlas might reflect these exotic conditions. Lower metallicity environments are known to produce different protoplanetary disks with different ice lines and different volatile distributions. Carbon dioxide might have become more abundant relative to water. It would have done so in stellar systems with different radiation environments, or in systems with different chemical abundances than what we have around our Sunday. Research into the thick disk stellar populations has shown that they formed during an epoch when the galaxy underwent major merger events. It was merging with smaller satellite galaxies at that time. These collisions are known to have triggered bursts of star formation, and they created the chaotic gravitational environment that scattered objects like 3 I divided by Atlas into the interstellar space. The object might represent the debris from planetary formation processes that were operating under dramatically different conditions, different from those in our own solar system, for example. Dating the thick disk stellar populations suggests that it formed during the era that astronomers call cosmic noon. This was approximately 2 to 3 billion years after the Big Bang. This period marked the peak of the star formation rates across the universe. It was when the first heavy elements were being incorporated into planetary systems, and the chemical evolution of galaxies was proceeding most rapidly. The implications of this extend far beyond a single wandering comet. They extend to questions about the abundance of such massive interstellar objects. 3 I divided by Atlas weighs 10 million times more than any of the previous interstellar visitors. This creates some statistical impossibilities that are challenging our understanding of what is roaming between all of the stars. The 7-mile diameter of this object translates to a huge mass, approximately 1 trillion kilograms of mass, assuming a certain density, a density that is similar to that of typical comet nuclei. This estimate makes this object comparable in mass to some of the largest asteroids that we have in our own solar system, and it is moving at speeds that dwarf anything that is gravitationally bound to our Sunday, comparing 3I divided by Atlas to the previous interstellar visitors reveals the scale. ʻOumuamua was the very first confirmed interstellar object. It measured roughly 400 meters in its length, and it had an estimated mass of around 10 million kilograms. Borisov was the first interstellar comet that we had ever found. It showed a nucleus diameter of approximately 1 kilometer, and it had a mass estimate of around 1 billion kilograms. 3I divided by Atlas is dwarfing both of these predecessors. It is dwarfing them by factors that strain our statistical credibility. The mathematics of object size distributions in space is known to follow power laws. These laws are able to predict the relative abundance of different-sized bodies. Small objects are known to vastly outnumber the large ones. The relationship typically shows 10 times more objects at each factor of 10 decrease. Finding 3I divided by Atlas after only 3 interstellar detections is a problem. It violates these statistical expectations by enormous margins. Professional astronomers have calculated that discovering an object of this size, it should require the detection of millions of smaller interstellar visitors first. The probability of finding such a massive object among the first few detections, it approaches a statistical impossibility under our conventional models. This huge mass discrepancy suggests that there are fundamental gaps in our understanding of either the interstellar object populations or the ejection mechanisms that are creating them in the first place. Perhaps giant planets are more efficient at ejecting large objects, more efficient than they are at ejecting smaller ones. This would create size distributions that are different from our expectations. Expectations that are based on our own solar system's asteroid and comet populations. Alternative explanations for this involve some selection effects. These effects could be making the large objects easier to detect. They would be easier to detect despite their lower abundance. The gravitational binding energy that is required to eject this object, it exceeds the energy that is available from most planetary interactions. Computer simulations have shown that removing objects this massive, it requires encounters with planets that are at least as large as Jupiter. And these encounters must occur under precisely defined geometric configurations that are able to maximize the energy transfer efficiency. More exotic ejection scenarios involve stellar binary systems where 2 stars are orbiting each other with periods that create resonance with the planetary orbits in the system. During specific orbital alignments, the gravitational forces can amplify. They can amplify to levels that are sufficient for ejecting massive objects. However, such mechanisms require some very fine-tuned initial conditions that may be rare in the typical stellar systems. The survival of 3I divided by Atlas during its long journey is also a factor. It is dependent on its very large size. Smaller objects are known to experience proportionally higher surface to volume ratios. This is what makes them so vulnerable to erosion by cosmic rays, and it makes them vulnerable to interstellar dust impacts. 3I divided by Atlas has maintained sufficient mass to preserve its internal structure and to preserve its chemical composition despite its extended exposure to the harsh interstellar environment. Current surveys for interstellar objects remain biased. They are biased toward detecting the larger and brighter objects that are able to reflect sufficient sunlight for our ground-based telescopes. 3I divided by Atlas might just represent the visible tip of a vast population of interstellar wanderers that remain below our detection thresholds. Yet even more puzzling than its incredible mass is the mathematical impossibility of its orbital alignment. 3I divided by Atlas is following a trajectory that is so perfectly aligned with our own solar system that random chance becomes a mathematically absurd explanation. The orbital inclination of 3I divided by Atlas has been measured. It is just 5 degrees from the ecliptic plane of our solar system. The ecliptic plane is the imaginary disk where the Earth and the other planets orbit. For comparison, most of the objects that are approaching from interstellar space, they should be arriving from completely random directions. This would create orbital inclinations that are distributed equally across all of the possible angles. Finding an interstellar visitor that is aligned so closely with our planetary system, it occurs with a probability of less than 0.2%. Understanding the orbital mechanics of this requires visualizing 3-dimensional space, where objects are able to approach from any direction on an imaginary sphere, a sphere that is surrounding our entire solar system. Random arrivals should be distributed uniformly across this sphere. Most of the trajectories would be inclined at very high angles relative to our own planetary orbits. 3I divided by Atlas instead is approaching nearly within the very same plane. The same plane that is occupied by the Earth, Mars, Jupiter, and Saturn. The mathematical analysis of this extends beyond just the simple inclination. It includes other orbital parameters that compound the statistical improbability. 3I divided by Atlas is approaching our Sun in what is known as retrograde motion. It is traveling in the opposite direction to how our planets orbit. Retrograde interstellar objects are something that we expect to see, but when this is combined with the very low inclination, the probability of this drops to levels that challenge a random occurrence. Professional statisticians and astronomers have calculated the combined probability of all of the observed orbital characteristics. The analysis includes the approach velocity and the inclination angle. It also includes the retrograde motion and the timing of the discovery. Multiple independent calculations have confirmed that such an alignment. It should occur less frequently than once per several thousand encounters. The timing aspect of this adds another layer of improbability. 3I divided by Atlas was discovered at an optimal distance and brightness, an optimal distance for a detailed study of the object. This has allowed for months of observations before it fades. The random discovery timing should be distributed uniformly. It should be uniform throughout the object's passage through our solar system. Yet this object appeared precisely when our ground-based telescopes could study it, could characterize it most effectively with their instruments. Some researchers have proposed the idea of anthropic selection effect. These effects could explain these statistical anomalies. Perhaps interstellar objects with orbital characteristics like this one. They are just more easily detected and studied by us. This would create an observational bias that makes such discoveries seem more common. However, the magnitude of the probability involved is very large. It exceeds the typical selection effects by several orders of magnitude. Alternative explanations for this invoke gravitational focusing mechanisms. These mechanisms might be able to preferentially direct interstellar objects, direct them towards some specific orbital orientations. The gravitational field of our galaxy is known to create subtle effects that could influence the trajectories of these objects, influence them over their billion-year-long timescales. However, detailed calculations have shown that these effects are too weak. They are too weak to be able to explain the observed orbital alignment. More speculative theories have suggested that 3I divided by Atlas might not be random. It might not represent a random interstellar wanderer at all, but it could instead originate from a stellar system with a specific relationship, a specific geometric relationship to our own solar system. Objects that are ejected from stellar systems in our local neighborhood, They might show some preferential orbital orientations. This would be due to their shared motion around the galactic center. The discovery sequence of these objects itself adds some statistical complexity. Finding 3 interstellar objects in less than a decade is a surprise. It is a surprise after centuries of astronomical observation. This suggests either a remarkable coincidence or systematic changes. Systematic changes in our detection capabilities and techniques. The rapid succession of these discoveries might indicate something. It might indicate that interstellar visitors are far more common than we thought. However, advanced space telescope observations would soon reveal something. They would reveal chemical signatures that defy all conventional explanations. The most powerful space telescope that has ever been built. It has revealed chemistry in this object that challenges the laws of physics. When the James Webb Space Telescope turned its instruments toward this object, it did so in August of 2025. Astronomers were expecting to confirm its basic comet chemistry. They were expecting to do so with improved precision and sensitivity. Instead, the Webb telescope detected some molecular signatures that are violating our fundamental expectations about matter, about how matter behaves in the space environments. The Webb telescope is able to operate in the infrared wavelengths. These wavelengths can penetrate the dust and gas to reveal molecular compositions that are invisible to our ground-based instruments. Its 18-segment primary mirror is larger than a tennis court. It can collect enough light to be able to analyze the chemical fingerprints, the fingerprints of objects that are billions of miles away. It can do so with unprecedented detail and accuracy. Webb's near-infrared spectrograph has created spatially resolved maps of the different molecules across the coma of this object. This has revealed how the various chemicals are distributed around the nucleus of the interstellar comet. The instrument has detected carbon dioxide concentrations that are 8 times higher than the water vapor in the comet's coma. This has confirmed the ground-based measurements that were made, and it has provided 3-dimensional information about the gas cloud. The spatial resolution capabilities of the Webb telescope have revealed something. The carbon dioxide emissions are concentrated in specific regions. They are concentrated around the nucleus, not distributed uniformly. This pattern suggests either highly localized surface composition variations, or it suggests an internal structure that is channeling the gas flow. Neither of these phenomena is matching our expectations. Our expectations for typical comet behavior under solar heating. Webb has also detected complex organic molecules in this object. It has done so with abundances and ratios that are different from any solar system comet that has been previously studied. The instrument has identified some carbon chain compounds. It has also found nitrile molecules and organic polymers. These suggest formation or processing under conditions that are absent in our local cosmic environment and neighborhood. The isotopic composition measurements have provided the most startling revelations. Webb's sensitivity allows for the detection of rare isotopic variants. These can reveal information about the formation conditions, and they can reveal information about stellar nucleosynthesis processes. 3I divided by Atlas shows isotopic ratios for carbon, nitrogen, and oxygen. Ratios that differ significantly from the solar system values, and they differ from the typical interstellar medium compositions. These isotopic signatures suggest that this object formed in a different environment, a stellar environment with different nuclear physics conditions, different than what exists around our own sun, for example. Perhaps the object has originated around a star with a different mass, a different metallicity, or a different evolutionary history, a history that has produced unique isotopic abundances. Webb's observations have also revealed temporal variations in the chemical emissions that are following unexpected patterns. Most comets are known to show smooth changes in their gas production. They do so as they approach and recede from their parent stars. 3I divided by Atlas instead is displaying erratic variations. Variations in the different molecular species that it is emitting. This suggests some complex internal processes are at work, or some structural changes are occurring during the solar heating. The temperature mapping capabilities of the Webb telescope have shown something. This object is maintaining surface temperatures that are consistent with the efficient sublimation of its carbon dioxide, while it is keeping its water ice below the sublimation thresholds. This thermal behavior requires an unusual surface composition, or it requires a structure that preferentially releases the carbon dioxide, while at the same time it is preserving the water in a solid form. Perhaps the most puzzling of all are the negative detections, the molecules that should be present but remain absent. Absent from the Webb telescope's sensitive observations. 3I divided by Atlas is showing no evidence of methane at all. It is also showing no evidence of ammonia or hydrogen sulfide. These are common volatile compounds that are found in most solar system comets. The absence of these materials suggests that it formed under different conditions, different chemical conditions from the typical comet-forming regions, but the strangest discovery would emerge from the measurements of its metallic elements, measurements that have sparked controversial theories about its artificial origins. 3I divided by Atlas is emitting metallic nickel vapor in patterns that have never occurred in nature, which is triggering debates about artificial manufacturing. The detection of atomic nickel emission from this object. It required the most sensitive ground-based spectrographs that were operating at their very detection limits. The Very Large Telescope in Chile used its adaptive optics systems. It used them to compensate for the atmospheric turbulence. This allowed it to achieve a resolution that was sharp enough to be able to separate the nickel emission lines, to separate them from the contaminating signals in the crowded optical spectrum. The nickel atoms in the coma of this object are emitting a green light, a characteristic green light at a wavelength of 527.03 nanometers. This happens when they are excited by the solar radiation. This emission line appears to be distinct from other metallic elements, and it provides an unambiguous identification of the nickel vapor. The signal from 3I divided by Atlas exceeded the background noise levels. It did so by factors that were sufficient to confirm a genuine detection. The intensity of the nickel emissions from this object. It increased by 25 times between July and August. It was following a steep mathematical progression that suggests systematic changes. Changes in the surface composition or the internal structure. This behavior differs dramatically from the typical cometary outgassing patterns. These patterns usually show smooth variations that are correlated with the solar distance. Laboratory studies of nickel-bearing meteorites and asteroid samples have shown something. Nickel typically occurs combined with iron in metallic alloys, or it is bound in the silicate minerals of the rocks. Releasing atomic nickel vapor requires heating these materials, heating them to temperatures that are exceeding 1000 degrees Celsius. This is far higher than the surface temperatures that are achieved by solar heating, achieved at the distance of this object from our Sunday. The complete absence of any iron emissions in the very same spectrum. It creates a chemical signature that is unknown in natural space environments throughout the entire observable universe that we can see. Nickel and iron are always found to appear together. They are in ratios that are determined by stellar nucleosynthesis. This process creates these elements through similar nuclear reactions. Separating nickel from iron requires industrial processes, or it requires extreme physical conditions that are absent in typical environments. On the Earth, the separation of nickel from iron involves high-temperature smelting. It involves electrochemical processing or specialized metallurgical techniques. These processes require a technological infrastructure and energy sources that are unavailable in the space environments. This is raising questions about how this object could produce similar signatures, how it could do so through purely natural mechanisms. Some researchers have proposed exotic mineralogy explanations for this. These involve rare nickel-rich compounds that might sublimate. They might sublimate at different rates than the iron-bearing minerals. However, no known mineral phases show the extreme fractionation between nickel and iron that is observed. The chemical behavior of this object is violating fundamental principles of thermodynamics and of material science. Alternative theories for this invoke unusual formation conditions in the stellar system where this object originated. Perhaps the magnetic field configurations during planet formation. Perhaps they created chemical separation mechanisms that are unknown in our solar system. Or the stellar radiation environments might have processed the surface materials. They would have done so through photochemical reactions that preferentially released nickel, while at the same time they were preserving the iron in non-volatile compounds. The time-variable behavior of the nickel emissions adds complexity. It challenges all of the proposed natural explanations. The 25-fold intensity increase follows mathematical patterns that are reminiscent of some systematic processing, and not the random geological or chemical phenomena. Such organized behavior typically indicates controlled mechanisms, controlled rather than chaotic underlying mechanisms. Harvard physicist Avi Loeb has noted that the nickel without iron signature, when it is combined with the orbital characteristics and the timing of the discovery, it creates multiple statistical anomalies that individually might occur naturally, but collectively they suggest a systematic rather than a random origin. His analysis has sparked public discussions about whether this object might be artificial. These speculative theories would soon require official responses from the space agencies. Responses from agencies that are concerned about public misconceptions. The space agencies have found themselves forced to publicly address the growing speculation. The speculation that 3-1 divided by Atlas might be an artificial technology from another distant civilization. The combination of its unusual orbital characteristics and its chemical signatures, and the statistical improbabilities that are surrounding this object, all of this has generated online theories that suggest an artificial origin. Social media platforms and astronomy forums have been buzzing with discussions that are comparing this object to science fiction depictions of alien spacecraft or automated probes. Harvard physicist Avi Loeb, who is known for his controversial suggestions, he has published detailed analyses that are suggesting that 3I divided by Atlas shows something. It shows multiple characteristics that are inconsistent with natural astronomical objects. His Loeb scale has rated this object as a 4 out of 10 for its artificial likelihood. This is based on its orbital alignment and its chemical anomalies, and the timing of its discovery, which individually might be natural, but collectively they suggest a systematic rather than a random phenomenon. The rapid spread of these theories through the internet communities, it has prompted some official responses from NASA and the European Space Agency, and from other major astronomical organizations as well. These institutions have recognized the need to address the public misconception. They must do so before the speculation overwhelms the scientific analysis, overwhelms it with unfounded claims about extraterrestrial visitation. NASA has issued some comprehensive statements about this. Statements that are explaining the natural phenomena that could account for the unusual characteristics of this interstellar object. The agency has emphasized that comet nuclei can develop complex internal structures, and they can develop complex chemical compositions over billions of years. They would do so in the interstellar space, creating different signatures that are different from the typical solar system objects. This would not require any kind of artificial origins. The nickel without iron emissions received particular attention. They received particular attention in the official statements. NASA scientists have explained that selective sublimation processes, they could be preferentially releasing certain metallic elements, while at the same time they are keeping others bound in thermally stable compounds. The agency has cited some laboratory studies of meteorite compositions, studies that show that rare mineral phases might be able to account for this, account for the unusual elemental ratios under specific heating conditions. The space agency responses have also addressed the statistical improbabilities, the improbabilities that are surrounding its orbital characteristics and discovery timing. Officials have noted that a detection bias can affect the interstellar object surveys. This can make objects with specific orbital orientations more likely to be discovered and more likely to be studied than those approaching from random directions. The apparent statistical anomalies might just be reflecting these observational selection effects and not any genuine improbabilities in the universe. Professional astronomers have emphasized the importance of applying the scientific method, applying it to analyze these unusual phenomena that we are seeing, and not jumping to any extraordinary conclusions about them, not without first exhausting all of the natural explanations. The scientific process requires testing the conventional hypotheses. It requires testing them before considering the more speculative alternatives. Even when we are dealing with genuinely anomalous observations, multiple independent research groups have confirmed that this object, it exhibits some normal cometary behavior, including dust emission. It also shows gas production and the development of a coma. These are all consistent with the solar heating of volatile materials. Infrared observations of the object have shown thermal signatures that are matching our expectations for a rocky and icy composition, while the photometric measurements have revealed its surface properties that are similar to those of other comet nuclei. Radio telescope searches for any artificial signals from this object. They have detected no emissions beyond the natural thermal radiation and the reflected sunlight from the surface of the object. The Search for Extraterrestrial Intelligence Institute has monitored the object. It has done so across multiple different frequency bands. It has done so without finding any evidence of technological activity or any evidence of communication attempts from the object. The scientific consensus that is emerging from the detailed analysis, it has concluded that 3I divided by Atlas represents an unusual but natural object, a natural interstellar comet with characteristics that have been shaped by its formation conditions and processing mechanisms that are different from the objects in our own solar system. The unusual properties of this object are reflecting the diversity of the planetary formation environments throughout our galaxy. They are not a sign of any kind of artificial construction. However, the approaching perihelion passage of this object will create opportunities, unprecedented opportunities for a detailed study of it. A study during the most dramatic phase of this cosmic visitor's journey. 3I divided by Atlas will reach its closest approach to our own Sunday, precisely when the Earth cannot observe the most dramatic moment. The most dramatic moment in this cosmic visitor's billion-year journey, the perihelion passage of this object is going to occur. It will occur on October 30th, 2025. This is when 3I divided by Atlas will reach its minimum distance from our Sunday, a minimum distance of 1.36 astronomical units. This distance will place the comet between the orbits of Earth and Mars. It will be closer to our star than any previous interstellar visitor has been, closer during the time of our human observation of the skies. However, the timing of this event is creating an astronomical tragedy, a tragedy of truly cosmic proportions for us here on Earth. During the October perihelion of this object, 3I divided by Atlas will be positioned directly behind the Sunday. It will be directly behind the Sun from our perspective here on Earth. This is creating what astronomers call a solar conjunction. The brilliant disk of our own Sun will completely overwhelm any light that is reflected from the surface of the comet. This will make any direct observation of it completely impossible with even the most powerful of our ground-based telescopes. This celestial alignment means that humanity will miss the peak activity phase, the peak phase when this object will reach its maximum gas production, and when it will potentially develop its largest and most spectacular tail. The physics of the perihelion passage promises some spectacular transformations that will remain completely hidden from our view. The solar heating of the object will intensify dramatically. It will intensify as 3I divided by Atlas is approaching the Sunday. This could potentially increase its carbon dioxide production rates. From the current levels of 129 kilograms per second, it could increase to several times higher values than that. The surface temperatures of the object could reach levels that are sufficient to be able to sublimate the water ice that is buried beneath the carbon dioxide-rich outer layers of the comet. Computer models have predicted that the perihelion heating might trigger something. It might trigger some structural changes in the nucleus of the object. This would happen as the internal pressure from the sublimating gases, as it creates stress fractures or some explosive outgassing events. Comet nuclei are known to occasionally fragment during close solar approaches. This happens when the internal heating is able to overcome the gravitational binding forces. This can create multiple, smaller objects with an enhanced surface area for their gas production. The tail development of the comet during its perihelion passage, it represents the most visually dramatic aspect that will be hidden from our Earth-based observation of the event. As 3I divided by Atlas approaches the Sun, the solar radiation pressure and the stellar wind interactions will accelerate the gas and dust. They will accelerate them away from the nucleus of the comet. This could potentially create tail structures that are extending for millions of kilometers out into space. This would rival the distance between the Earth and the Sunday. The retrograde orbital motion of this object might produce unusual tail orientations that are different from the typical solar system comets. Ground-based observatories have planned some coordinated observation campaigns. They have planned them for September and November of that year. This will be bracketing the hidden perihelion passage. It will be doing so with detailed measurements of the pre- and post-perihelion activity. These observations will be able to document the changes in the gas production. They will document the dust emission rates and the chemical composition. This will reveal information about its internal structure and heating mechanisms. The solar conjunction problem is going to affect all of our Earth-based telescopes. It will do so regardless of their size or their location. Space-based observatories like Hubble and James Webb also face similar limitations. They do so when they are observing objects that are positioned too close to the Sunday, the solar panels and the sensitive instruments on these telescopes. They must be protected from the direct solar radiation. This is what prevents the observations of targets within certain angular distances from our own star, the Sunday. Radio telescopes can potentially observe this object during the solar conjunction. They can do so by detecting its thermal emissions at certain wavelengths where the Sun appears to be less bright relative to other sources. However, the radio observations can provide only limited information about the chemical composition and the structural details. This is compared to the optical and the infrared measurements that require direct imaging capabilities to be made. The timing of the solar conjunction represents an astronomical misfortune, a misfortune that is compounded by the rarity of these interstellar visitor encounters. Humanity might have to wait for many decades or even centuries. Wait before another object of a comparable size and scientific interest, an object that will approach our own solar system in the future. This is what makes the observational gap during the perihelion passage. It makes it particularly frustrating for all of the researchers who are studying the interstellar comet behavior. Fortunately, the spacecraft that are positioned throughout our solar system, they will be able to provide some unique viewing opportunities that will be unavailable from here on the Earth. The spacecraft that are orbiting the planet Mars will capture humanity's only close-up views of this object during its most active and dangerous phase. The Mars Reconnaissance Orbiter is one of these spacecraft. Europe's Mars Express and the ʻOumuamua Trace Gas Orbiter are others. They will be occupying perfect positions to be able to observe this object. They will do so during its October close approach to the red planet. These robotic sentinels will be able to achieve viewing angles that are completely impossible from the Earth. They could potentially be able to provide 3 times better resolution than the Hubble Space Telescope observations. They will do so during the comet's peak activity period. Mars will reach its opposition to this object on October 3rd. This will be positioning the planet optimally for detailed observations. It will happen when the interstellar visitor is passing within 47 million kilometers. 47 million kilometers of the red planet itself. This distance represents a closer proximity than the object will achieve to Earth. This will create some unprecedented opportunities for high-resolution imaging. And it will create opportunities for spectroscopic analysis of the object. The Mars Reconnaissance Orbiter is carrying a powerful camera, the High-Resolution Imaging Science Experiment camera. It is capable of resolving surface features that are smaller than 1 meter across. It can do so on the surface of Mars from its orbital altitude. When it is pointed toward 3i divided by Atlas, this instrument could do something. It could potentially be able to detect the structural details in the comet's nucleus and map the 3-dimensional architecture. The architecture of its gas and its dust emissions with a high resolution, a resolution that is impossible from our Earth-based telescopes. Europe's Mars Express orbiter will contribute some complementary capabilities. It will do so through its visual and infrared mineralogical mapping spectrometer. This instrument was designed to analyze the surface compositions on Mars. This instrument is able to identify specific minerals and chemical compounds. It can do so in this object across a wide range of wavelengths that are optimized for detecting water and carbon dioxide, and also the organic molecules that can reveal information about its formation. The ʻOumuamua Trace Gas Orbiter is specializing in atmospheric chemistry. It is using some ultra-sensitive spectrographs to do this. It was originally designed to search for the trace gases in the Martian atmosphere. These instruments are able to detect molecular concentrations at parts per billion. This could potentially reveal some minor chemical species in the object, species that remain below the detection thresholds for our Earth-based observations. Coordinated observations from the multiple Mars orbiters will create something. They will create stereoscopic imaging opportunities that can reveal the structure, the 3-dimensional structure, and the motion within the coma of this object. By comparing the simultaneous images from different viewing angles, researchers will be able to map the gas flow patterns. They will be able to map the dust particle trajectories and the internal structure, details that are impossible to determine from single perspective observations. The Perseverance and Curiosity rovers on the surface of Mars might detect something. They might detect atmospheric changes that are caused by the dust and the gas. The dust and the gas from this object that is entering Mars's thin atmosphere. They're sensitive instruments that are designed to monitor the Martian atmospheric chemistry. They could potentially be able to identify some trace contamination from this interstellar visitor, providing ground truth measurements of the chemical composition and the particle size distributions. The Mars orbiters will be facing some unique challenges. They will face them when they are observing this object. This is due to their own orbital motion around the red planet. The spacecraft must be able to maintain a precise pointing accuracy. They must do so while they are moving at orbital velocities that are exceeding 3 kilometers per second. This will require some sophisticated guidance systems to track the fast-moving target. The timing of the Mars observations is coinciding with the dust storm season. The dust storm season on the surface of the red planet. The atmospheric opacity during this time can interfere with the surface-based measurements. However, the orbital altitude of these spacecraft places them above most of this. It places them above most of the atmospheric effects. This will provide them with clear viewing conditions for their observations. This will be regardless of the surface weather conditions on Mars. The data transmission from Mars to the Earth will require some careful scheduling. This is to avoid the interference from the solar conjunction effects that will also be impacting the communications with the interplanetary spacecraft. The Mars orbiters will have to store their observational data on board. They will do so until the communication windows are able to provide a reliable downlink, a downlink that will allow them to transmit their high-resolution images and spectra. These Mars observations will be able to document the activity levels. The activity levels during the cosmic noon phase of this object's evolution. 3I divided by Atlas is carrying pristine materials from the cosmic noon, the epoch when the star formation in our universe peaked, and the very first of the heavy elements had just emerged. The cosmic noon is a period that occurred approximately 2 to 3 billion years. 2 to 3 billion years after the moment of the Big Bang. It marked the era when the galaxies were forming their stars at very high rates that were 10 times higher than what we see today, and the universe was undergoing its most dramatic period of chemical evolution. During this particular epoch, the first generations of massive stars, they had completed their entire life cycles in a short time. They were exploding as supernovas that were scattering their heavy elements. They were scattering them throughout the vastness of space. These elements would then be incorporated into the subsequent stellar and planetary systems. The age estimates for this interstellar object place its formation. They place it during or shortly after the cosmic noon. This is what makes this interstellar visitor a direct sample. A direct sample of the materials that were processed during the universe's most dynamic phase. The chemical signatures that have been observed in its spectroscopic analysis. They are reflecting the conditions that existed when the galaxies were younger, when they were much more active and chemically different from the present-day cosmos that we see around us. Understanding the cosmic noon requires appreciating the scale of universal evolution, the evolution that has occurred over the 13.8 billion years, the years that have passed since the moment of the Big Bang. The very earliest of the stars were formed from primordial hydrogen and helium. They were lacking the heavy elements that are necessary for rocky planet formation. Only after several generations of stellar evolution had passed did sufficient amounts of carbon, oxygen, silicon, and iron accumulate in the interstellar space to enable complex chemistry and to enable the development of the planetary systems. The metallicity measurements of 3I divided by Atlas have shown something. They have shown heavy element abundances that are consistent with cosmic noon. These concentrations are falling below the solar values that we see, but they are exceeding those of the very earliest stellar generations. This indicates that it formed during the transitional epoch, the epoch when the heavy element enrichment was progressing rapidly. It was progressing through the galactic chemical evolution processes. The star formation rates during the cosmic noon were much higher. They exceeded the current galactic activity by factors of 10 to 100. This created environments where the stellar feedback processes were operating. They were operating under dramatically different conditions than what exists today. Higher supernova rates and more frequent stellar collisions. and the intense radiation fields from the massive stellar associations. All of this created chemical processing mechanisms that are absent in the present-day galactic environments that we can observe. The thick disk stellar population from which this object likely originated. It was formed during the cosmic noon through processes that are poorly understood, galaxy merger events, and the gas accretion from intergalactic space, and the gravitational instabilities in the early galactic disks. All of this created the bursts of star formation that established the properties, the chemical and the kinematic properties that are observed in the thick disk today. The protoplanetary disks that were forming during the cosmic noon, they were operating under different physical conditions than those around present-day stars. Higher background radiation levels and different dust grain compositions and altered ice line locations could have produced different planetary systems with chemical architectures that are unlike anything in our local neighborhood. 3I divided by Atlas might just be representing the materials that were formed under these conditions. The isotopic ratios that have been measured in this object, they are reflecting the nuclear physics processes that were occurring in the stellar interiors during the cosmic noon. Different types of stars were dominating the stellar populations at that epoch. This included the massive stars with their very short lifespans. These stars were contributing disproportionately to the heavy element production. They were doing so through their rapid evolutionary sequences that were ending in the powerful supernova explosions. Laboratory studies are not able to replicate the cosmic noon conditions. This is due to the vast scales of energy, time, and gravitational influence. All of the things that are involved in the galactic chemical evolution. 3I divided by Atlas is providing us with direct access to the materials that were processed during this very crucial epoch. It is offering some unique insights into the physical processes, the processes that have shaped the chemical foundation for all subsequent planet formation. The survival of 3I divided by Atlas over the billion-year timescales. It has preserved the chemical signatures that would otherwise remain inaccessible. This interstellar time capsule is carrying information about the cosmic noon. It is also carrying information about stellar nucleosynthesis and about the protoplanetary disk chemistry and the early planetary formation processes. All of this is frozen in its internal structure and composition. These ancient materials are challenging our fundamental assumptions. Our assumptions about how the planetary systems are developing throughout the entire history of the cosmos. 3I divided by Atlas is demolishing our textbook models of how planets are formed. It is revealing that our own solar system represents a cosmic anomaly rather than the typical behavior. Traditional planetary formation theory is assuming something. It assumes that the protoplanetary disks around young stars follow predictable patterns where the water ice is dominating the volatile inventories. It is doing so beyond specific distances that are called the ice lines. 3I divided by Atlas is inverting this fundamental assumption completely. It is doing so with its extreme carbon dioxide to water ratio of 8:1. This suggests that it formed in an environment where carbon dioxide ice was more abundant than the water ice during the planet-building processes. The standard model of planetary formation begins with the stellar nebulae. These are collapsing under gravity to form the central stars. These stars are surrounded by rotating disks of gas and dust. As the temperatures are decreasing with the distance from the central star, different volatile compounds are known to freeze out. They do so at very characteristic and specific locations. Water ice will freeze out beyond approximately 3 astronomical units. Carbon dioxide ice will freeze out much farther out from the star, and other compounds will freeze out at even greater distances. 3I divided by Atlas appears to be violating these ice line predictions. It is violating them completely with its strange chemistry. Its chemical composition is suggesting that it formed in a region a region where the carbon dioxide was remaining more abundant than the water. It was doing so throughout the entire planet formation process. This would require environmental conditions that are absent in our solar system, and they are absent in most of our theoretical models. Models of the typical protoplanetary disk evolution. Computer simulations of the protoplanetary disk chemistry have shown something. Achieving carbon dioxide dominance over water requires unusual stellar properties. It requires unusual disk compositions or radiation environments. Perhaps 3I divided by Atlas was formed around a star with a different luminosity, a different surface temperature, or a different evolutionary history. A history that has altered the thermal structure and the chemical gradients, the gradients that were within its surrounding protoplanetary disk. Alternative scenarios for this involve some stellar systems that have different heavy element abundances. This would affect the dust grain compositions and the gas phase chemistry. Stars that have metallicities that are significantly lower or higher than the Sunday. They might be able to produce protoplanetary disks with altered volatile inventories. This would be creating the conditions where the carbon dioxide becomes more abundant than the water in the planet-forming regions. The implications of this extend far beyond just the individual object chemistry. They extend to fundamental questions about the diversity of planetary systems, the diversity throughout the entire galaxy that we live in. If 3I divided by Atlas is representing the typical materials from stellar systems that were formed during the cosmic noon, then billions of planetary systems might have developed chemical architectures that are completely different from our own solar system's organization. This incredible chemical diversity is suggesting that habitable planet formation, it might be following pathways that are unknown in our local cosmic environment. Planets that are forming in carbon dioxide-rich environments. They could be developing atmospheres and surface conditions, and they could be developing potentially biological processes that are based on chemical foundations that are different from Earth, different from the Earth-based life that depends on liquid water. The survival and the ejection of this object also reveals information about the dynamical processes in its parent planetary system. Objects that have unusual chemical compositions might experience different interactions, different gravitational interactions with the forming planets. This would affect their final orbital distributions, and it would affect their ejection probabilities as well. This would be compared to the typical solar system analogues. Recent exoplanet discoveries have shown us that planetary systems throughout the galaxy are displaying a huge diversity, a diversity that is far exceeding our early theoretical predictions. Hot Jupiters that are orbiting very close to their stars, super-Earths that are lacking any solar system analogues, and unusual orbital configurations are suggesting that planet formation, it is operating under a much broader range of conditions than we thought. 3I divided by Atlas is providing us with direct chemical evidence that is supporting this idea of diversity. It is carrying materials that were formed under conditions that are absent in our own solar system and our own neighborhood. The object is representing a messenger from the planet formation processes that are operating according to physical principles and environmental parameters that are different from those that created the Earth. Understanding the formation history that is encoded in this object, it requires a detailed laboratory analysis of its materials that will never be available for us to study directly. The object will continue on its journey into interstellar space. It will be taking all of its chemical secrets with it. It will be taking them beyond the reach of our spacecraft missions, or any sample return opportunities in the future. Yet these ancient materials might be playing an active role in the seeding of planetary formation, the seeding of it around the young stars throughout our galaxy. 3I divided by Atlas is preserving materials that are older than our entire solar system. It is preserving them in a chemically pristine condition. This is creating a kind of a traveling laboratory of primordial cosmic materials. The 7 to 14 billion year age estimates for this object. They mean that this object is containing materials that were formed when the universe was less than half of its current age. These ancient substances have been able to survive for billions of years. They have survived their exposure to the cosmic radiation and to the interstellar chemistry and the gravitational perturbations, while at the same time they are maintaining their chemical signatures that are recognizable to our modern spectroscopic analysis. The preservation of these primordial materials requires protection from the processes that normally alter or destroy the chemical compounds, over the long geological timescales. Cosmic ray bombardment is known to create nuclear transmutation reactions. These reactions are able to change the elemental compositions. Ultraviolet radiation from the distant stars is able to break the chemical bonds. The chemical bonds that are in the organic molecules, impacts with the interstellar dust particles, can erode the surface layers, and they can mix the materials from different formation epochs. The large size of this interstellar object provides crucial protection. It does so through its favorable surface to volume ratios. These ratios are able to minimize the external processing. They are able to do so relative to the internal preservation. Small interstellar objects are known to experience proportionally higher surface exposure. This is what destroys their primordial signatures within millions of years. 3I divided by Atlas has maintained sufficient bulk to preserve its internal materials. It has preserved them from the cosmic ray penetration and the surface erosion. The temperature conditions during its interstellar travel have also favored preservation. The nucleus of this object has remained at temperatures that are approaching absolute zero. It has done so throughout its billion-year journey. This has effectively frozen all of its chemical reactions, and it has prevented any thermal processing that would alter its composition. This deep freeze has preserved the volatile compounds, and it has preserved the organic molecules that would decompose under any warmer conditions that it might encounter. Laboratory studies of the meteorites and the lunar samples have shown us something. The space weathering processes can alter the surface compositions. They can do so within just thousands to millions of years of exposure. 3I divided by Atlas has endured exposure times that are orders of magnitude longer, while at the same time it has preserved its chemical signatures that are detectable through our modern observational techniques. This suggests some unusual protective mechanisms are at work, or its formation with exceptionally stable material compositions. The chemical analysis that has revealed the complex organic molecules and the unusual isotopic ratios and the exotic volatile compositions, it indicates that this object is carrying direct samples of the primordial materials from its formation epoch. These signatures are representing a kind of fossilized chemistry from the stellar nucleosynthesis processes and from the protoplanetary disk evolution and the early planetary formation mechanisms that were operating under conditions that are different from our solar system. The isotopic measurements are providing the most robust evidence for this. Different isotopes of the same element are known to form through specific nuclear physics processes in the stellar interiors. This creates signatures that can persist through subsequent chemical processing, unless they are altered by the nuclear reactions. 3I divided by Atlas is showing isotopic ratios that are reflecting the stellar nucleosynthesis, the conditions of it from its own formation epoch. The organic chemistry that has been detected in this object, it includes some carbon chain molecules and some nitrile compounds. These are compounds that typically decompose under cosmic ray bombardment. They do so within just a few millions of years. Finding these compounds after a billion-year interstellar exposure suggests something. either its formation with unusually stable organic compositions or some protection mechanisms that have prevented the radiation damage. Comparison with our own solar system materials reveals the extent of this, the extent of the chemical preservation in this object. Meteorites that are from our own asteroid belt were formed 4.6 billion years ago. They show an extensive alteration from the solar heating and from the planetary interactions and the space weathering processes. 3I divided by Atlas is preserving signatures from potentially twice this age, while at the same time it is maintaining less alteration than typical objects. The pristine nature of the materials in this object, it is creating some unique opportunities for studying the cosmic chemical evolution, studying it through direct observation rather than theoretical modeling. This interstellar visitor is providing us with access to formation conditions and to processing mechanisms that remain otherwise inaccessible to our observational astronomy or our laboratory investigation. These preserved ancient materials might be actively participating in the creation of the next generation of planetary systems. 3I divided by Atlas might be functioning as a kind of a galactic seed pod, a seed pod that is carrying the building blocks that are needed to be able to jumpstart the planet formation around infant stars. Recent theoretical work by Suzanne Falsner and her colleagues has suggested something. Interstellar objects like this one could be solving fundamental problems in our planetary formation theory. They could be doing so by providing some ready-made building blocks for the planetary accretion around the young stellar systems. Traditional models are known to struggle to explain how the microscopic dust particles, how they are able to grow to the planetary sizes that we see, how they do so without being swept into the central stars. The meter barrier problem in planetary formation theory, it describes the difficulty of growing objects from centimeter to kilometer sizes. It describes the difficulty of doing so through collisional processes. Objects that are in this particular size range, they are known to experience a strong aerodynamic drag from the gas that is in the protoplanetary disks that they are in. This is what causes them to spiral inward toward the central stars. They do so faster than they can grow through the accumulation of more material. 3I divided by Atlas is able to bypass this barrier completely. It is doing so by providing some pre-assembled kilometer-sized building blocks. Computer simulations have shown that interstellar objects that are captured by the young stellar systems, they can significantly accelerate the giant planet formation. They can do so by serving as condensation nuclei for the gas and the dust accretion. Objects that are the size of 3I divided by Atlas are able to provide gravitational seeds that are able to attract the surrounding material. They can do so more efficiently than trying to build the planets from scratch through the gradual accumulation processes. The chemical composition of this object offers some additional advantages for the seeding of planetary formation. Its unusual carbon dioxide to water ratio might provide something. It might provide volatile inventories that can complement rather than duplicate the materials that are already present in the typical protoplanetary disks. This chemical diversity could be able to enhance the range of planetary compositions and the range of the atmospheric architectures that are possible in the young and forming stellar systems. The capture of these interstellar objects requires some precise gravitational dynamics. It requires this during the encounters with the stellar systems. The objects must be able to lose a sufficient amount of their velocity. They must do so to become gravitationally bound to the star, while at the same time they are avoiding a direct collision with the central stars, or they are avoiding an ejection through subsequent planetary interactions. The probability of a successful capture will depend on the stellar system architecture. It will also depend on the gas disk properties and the encounter geometry. The massive size of 3-1 divided by Atlas is increasing its capture probability. It is doing so compared to the smaller interstellar objects. Larger objects are known to experience stronger gravitational focusing effects. These effects are able to enhance the interaction cross-sections with the stellar systems. The gas drag from the protoplanetary disks is able to provide more efficient energy dissipation. It can do so for the massive objects, increasing the likelihood of them achieving bound orbits around the central stars. Statistical models of the interstellar object populations have suggested something. The stellar systems are encountering potential seed objects. They are doing so frequently enough to significantly impact the planet formation processes. If interstellar wanderers like this one are common throughout the galaxy, then most of the young stellar systems might be incorporating external materials. They would be doing so during their planet formation epochs. The survival of 3-1 divided by Atlas during its billions of years of interstellar travel. It is demonstrating that such objects can maintain their structural integrity, and they can maintain their chemical composition throughout their journeys. This preservation capability is what ensures that the seeding materials, that they are able to retain their original properties when they are incorporated into the new planetary formation environments. Laboratory studies of the meteorites have shown us that our own solar system, it has incorporated materials from multiple different stellar sources. It did so during its formation 4.6 billion years ago. The isotopic signatures that are found in the primitive meteorites, they are revealing the contributions from different types of stellar nucleosynthesis. This is indicating that our planetary system was formed from chemically diverse ingredients. It was not formed from purely local materials at all. The seeding hypothesis is suggesting that planetary formation throughout the galaxy might be involving a systematic mixing of the materials from different stellar environments. This would happen through the process of interstellar object exchange. This process could be creating planetary systems with a chemical diversity, a diversity that is exceeding what individual stellar systems can produce. They can produce through their local planet formation processes alone. Understanding this galactic recycling network will require some coordinated observations that will be made by multiple space-based observatories. Every major space observatory in human history is simultaneously tracking this object. It is tracking 3I divided by Atlas in the most coordinated scientific investigation, the most coordinated investigation that has ever been attempted. The international response to this object has triggered unprecedented cooperation among the space agencies and the research institutions, and the observatory networks that normally compete for limited observing time and for the limited resources that are available to them. Over 30 major telescopes have redirected their research programs. They have redirected them to focus on this one single target. This is creating the largest coordinated astronomical observation campaign, a campaign that has ever been seen in all of human history. The coordination of this effort began within hours of the initial discovery, the initial Atlas discovery announcement that was made. When the International Astronomical Union issued its alerts, it did so through the Minor Planet Center's communication network. This system is able to automatically notify the observatories. It notifies them worldwide about the newly discovered objects that will require follow-up observations to confirm their nature and to calculate their accurate orbital trajectories. Ground-based observatories from Hawaii to Chile have contributed. They have contributed observations using a wide range of instruments, from small survey telescopes to massive mirror arrays that are exceeding 10 meters in their diameter. The Very Large Telescope and the Keck Observatory, the Subaru Telescope and the Gemini Observatory have coordinated. They have coordinated their observing schedules to provide continuous coverage of this object as it is moving across the sky. It is moving across the sky from different geographical perspectives. Space-based assets, including the Hubble Space Telescope and the James Webb Space Telescope, have allocated their precious observing time that is normally reserved for studying the distant galaxies, and for studying the exotic astrophysical phenomena. These facilities are able to provide capabilities that are unavailable to the ground-based instruments that we have. This includes ultraviolet spectroscopy and infrared imaging at wavelengths that are blocked by the Earth's atmosphere. The European Space Agency's Gaia mission has been used. It was designed to map the stellar positions throughout our galaxy. It has provided some precise astrometric measurements of this object. Measurements of its position and its motion across the sky. This data is enabling some accurate trajectory calculations, and it is helping to determine the object's origin. Its origin within the galactic coordinate system. Gaia's unprecedented measurement precision allows for the detection of subtle gravitational perturbations that can reveal information about the internal mass distribution of the object. The Mars orbiters, including NASA's Mars Reconnaissance Orbiter and Europe's Mars Express and the ExoMars Trace Gas Orbiter, they have all received some special instructions to observe this object. They will observe it during its October approach to the red planet. Coordinating all of these observations has required some complex orbital mechanics calculations to ensure the spacecraft pointing accuracy while they are maintaining their primary mission objectives. Deep space missions, including the Europa Clipper and JUICE, and the Lucy and the Psyche missions have contributed. They have contributed observations from their unique vantage points that are scattered throughout our solar system. These spacecraft are able to provide viewing angles that are impossible from the Earth or from the Mars orbit. This is enabling a stereoscopic analysis of the object's structure and its composition from multiple different perspectives. The Swift Observatory, which was originally designed to detect gamma-ray bursts, it has redirected its sensitive ultraviolet instruments. It has done so to analyze the gas emissions from this object. This mission is demonstrating the flexibility of our modern space observatories, their ability to adapt their capabilities for unexpected scientific opportunities. Radio telescopes, including the Very Large Array and the ALMA Observatory and the Green Bank Telescope, have all searched for emissions at wavelengths where this object might be producing signals through natural physical processes or potential artificial origins. These facilities are able to provide complementary information about the thermal properties and the magnetic field interactions. These are things that are invisible to our optical instruments. Data sharing protocols that were established for this campaign, they have required the developing of new standards for coordinating the observations and processing the measurements, and for distributing the results among the international research teams. The unprecedented scale of the cooperation has created some logistical challenges in managing the telescope, scheduling, and the data transfer, and the scientific analysis across multiple institutions and countries. The coordination is revealing just how statistically impossible finding objects like this one should be. Mathematical analysis has proven that discovering 3I divided by Atlas, it is violating every single statistical model that we have. It is doing so by margins that are approaching impossibility. Professional astronomers are able to calculate the object discovery rates. They do so by using what are known as power law distributions. These distributions are able to predict the relative abundance of the different sized bodies throughout space. These mathematical relationships have been confirmed by decades of surveys of the asteroids and the comets within our own solar system. They have shown that the small objects are vastly outnumbering the large ones. They are doing so according to some very predictable ratios. Finding 3I divided by Atlas after only 3 interstellar detections, it is breaking all of these established statistical laws. The size distribution of the interstellar objects should be following similar patterns to our local asteroid and comet populations. It should have approximately 10 times more objects at each factor of 10 decrease, a decrease in the diameter of the objects. Under these kinds of assumptions, discovering a 7-kilometer wide a visitor like this one should require first detecting millions of smaller objects in the 100-meter to 1-kilometer size range. Our current interstellar object detection capabilities are remaining biased. They are biased toward finding the larger and the brighter targets that are able to reflect sufficient sunlight for our ground-based telescopes. However, even if we account for these observational biases, the probability of discovering this object among the first few detections, it is approaching a statistical impossibility under our conventional models. Independent research groups have calculated similar probability estimates. They have done so using different mathematical approaches, and they have used different survey simulation methods to do so. Monte Carlo computer models that are simulating thousands of potential discovery scenarios. They are consistently showing that finding objects of this size, it should occur less than once per several million encounters. It should do so under the conditions of random sampling. The rapid succession of the interstellar discoveries that have been made since 2017. It is also violating our statistical expectations for the detection rates. Astronomical surveys have been operating for many decades. They have been doing so without confirming any interstellar visitors. Then suddenly they have detected 3 of these objects within just 8 years. This clustering of discoveries is suggesting either a remarkable coincidence, or it is suggesting some systematic changes in our survey capabilities. Survey efficiency improvements that have been made through machine learning algorithms, and through the automated detection systems are increasing the probability. They are increasing the probability of finding these objects, but not by factors that are sufficient to explain the statistical anomalies. Modern surveys are achieving perhaps 10 times better detection rates, better than the previous generations of astronomical instruments. This is far below the improvement that would be needed to make such discoveries. To make such discoveries statistically reasonable for us, the orbital characteristics of this object are compounding the statistical problems. They are doing so through some additional improbabilities that are multiplying rather than adding to the overall detection odds. Objects that are approaching from random directions in space, they should be showing a uniform distribution of their orbital inclinations and of their velocities and their approach geometries. 3I divided by Atlas is clustering near the ecliptic plane of our solar system. It is doing so with a timing that is maximizing our observational opportunities. Alternative explanations for this are invoking some fundamental errors in our current understanding of the interstellar object population statistics. Perhaps the ejection mechanisms from the planetary systems. They are preferentially launching the large objects rather than the small ones. This would be creating size distributions that are different from our solar system. Or the gravitational focusing effects might be concentrating the interstellar visitors, concentrating them in specific regions of space that are increasing the encounter rates. More exotic theories are suggesting that 3-1 divided by Atlas represents a member of an unusual population of interstellar objects with characteristics that are different from the typical ejected comet, objects that have been formed through alternative mechanisms. They might be showing size distributions and chemical compositions and orbital properties that are violating our expectations. The statistical analysis of this is extending beyond the individual object properties. It is extending to the population-level questions about the abundance and the distribution of the interstellar wanderers. Current estimates are suggesting that approximately one interstellar object, an object that is larger than 100 meters in diameter, it is passing through our solar system on an annual basis. Yet the detection of these objects remains extremely challenging. This is due to their very high velocities and their faint brightness levels. These statistical impossibilities are paling in comparison to the exotic chemistry. The exotic chemistry that has been revealed through the detailed spectroscopic analysis. 3I divided by Atlas is carrying some deadly cyanide compounds. It is doing so in concentrations that are revealing its formation under chemical conditions that are unknown in our cosmic neighborhood. Ultraviolet spectroscopy from the Swift Observatory has detected something. It has detected the characteristic emission lines of the cyanide molecules. It has done so in the coma of this interstellar object. This is adding another layer of chemical mystery to this object, an object that is already defying our conventional understanding of comets. Cyanide is appearing as some sharp spectral features at specific ultraviolet wavelengths of light. This happens when the molecules are getting excited by the solar radiation, and they are then re-emitting the light at certain frequencies. The detection of this has required some sophisticated analysis techniques that can separate the cyanide signals from the contaminating emissions. The emissions that are from the other molecules that are present in the comet's coma. Cyanide is known to produce relatively weak spectral lines. They are weak compared to the major species like carbon dioxide. This is demanding some long exposure times with our sensitive instruments. This is necessary to achieve a sufficient signal-to-noise ratio, a ratio that will allow for a confident identification. Cyanide in the space environments is typically formed through chemical reactions that are involving both carbon and nitrogen. They happen under specific temperature and pressure conditions. The presence of the cyanide in this particular object is suggesting something. Either its formation in the regions of its parent protoplanetary disk, regions where such chemistry was occurring naturally, or its subsequent processing during its billions of years of interstellar travel. Processing that has created these compounds through alternative reaction pathways. The concentration levels of the cyanide relative to the other species, they are providing us with clues about its formation history, and they are providing clues about its chemical processing mechanisms. 3I divided by Atlas is showing cyanide abundances that are consistent with its formation in cold and dense molecular cloud environments. This is where the carbon and the nitrogen can combine efficiently. They can do so without any interference from competing chemical reactions that are occurring under different physical conditions. Laboratory studies of the stability of cyanide under space conditions, they have shown that these molecules are typically decomposing. They are decomposing when they are exposed to the ultraviolet radiation, or when they are exposed to the cosmic ray bombardment over time. Timescales that are much shorter than the age of this object. Finding stable cyanide compounds after a billion-year interstellar exposure, it is suggesting either some unusually stable molecular configurations or some protection mechanisms that have prevented its photochemical destruction. Cyanide is also known to appear in the spectra of some solar system comets, but it is typically at much lower concentrations than what we see here, and it is with different isotopic ratios than what has been observed. The unusual abundance patterns are suggesting its formation under nitrogen chemistry conditions that are different from those in our local planetary formation environment. This could be reflecting different stellar nucleosynthesis histories, or it could be reflecting different protoplanetary disk compositions. The biological significance of the cyanide detection is adding complexity. It is adding complexity to the discussions about potential habitability, the habitability implications of the interstellar object chemistry. While cyanide is highly toxic to most of the Earth-based life forms, it can also serve as a building block for more complex organic molecules. molecules that could contribute to prebiotic chemistry. Alternative formation pathways for cyanide are involving high-energy processes like the shock chemistry from the supernova explosions or from the stellar collision events that can create extreme pressure and temperature conditions that are capable of driving reactions. 3I divided by Atlas might be carrying the chemical signatures of violent events. Violent astrophysical events that occurred during its formation epoch. The time-variable behavior of the cyanide emissions from this object. It is showing patterns that are different from the other molecular species. This is suggesting some complex chemical processes are occurring within the comet's nucleus as the solar heating is progressing. Some of the molecular species are showing correlated variations, while others, including the cyanide, are displaying independent behavior. This is indicating that there are distinct source regions or formation mechanisms. Isotopic analysis of the cyanide molecules could provide some additional constraints on the formation conditions and the processing history. But such measurements would require a spectroscopic resolution and sensitivity, a resolution that is beyond our current observational capabilities. Future observations with more powerful instruments might be able to reveal this. They might reveal the isotopic signatures that can distinguish between the pathways. The cyanide detection, when it is combined with the other chemical anomalies, it is pointing toward the most spectacular finale for this object. As 3I divided by Atlas is approaching its own death in our solar system, 3I divided by Atlas will create the largest comet tail in all of recorded history. It will do so as it dies in a spectacular display of light, a display that will be visible across the entire solar system. The massive size and the unusual chemistry of this object, they are combining to produce a tail development potential, a potential that is exceeding any comet that has been previously observed by our human civilization throughout its history. Computer models have been predicting that the peak gas and dust production, it will occur during the perihelion passage of this object. It could create tail structures that are extending over 100 million kilometers out into the vastness of space. This would be rivaling the distance between the Earth and the Sunday. Comet tails are known to form through the interaction of solar radiation and the interaction of the stellar wind with the gas and the dust particles, the particles that are expelled from the comet's nuclei during the solar heating. The radiation pressure from the sunlight is able to push the smaller particles. It pushes them away from the sun, creating the characteristic curved tail, a curved tail structure that always points away from the central star. It does so regardless of the comet's own motion direction. The extreme carbon dioxide production rates that have been measured in this object, they are suggesting that the perihelion heating will trigger massive gas releases that will be dwarfing the typical solar system comet activity. The 129 kilograms per second of current carbon dioxide production. It could increase by factors of 10 or even more as the solar heating intensifies. This would be creating some unprecedented volumes of gas for the tail formation. The retrograde orbital motion of this object is producing some unusual geometry for the development of its tail. This is compared to the typical solar system comets that orbit in the same direction as the planetary motion in our solar system. Retrograde motion is known to create relative velocities that can enhance the interactions, the particle interactions with the solar wind, potentially producing tail orientations and tail morphologies that have never been observed in detail before. The dust particle analysis from the early observations has shown something. This object is producing grain sizes and compositions that are different from the typical solar system comets that we have seen. The unusual surface chemistry of this object might be creating dust populations with altered optical properties that can reflect light. They can scatter and absorb the sunlight differently than normal comet dust. This could potentially be producing some different tail colors and brightness levels. Unlike the previous comet displays that we have seen, the 7-kilometer diameter of the nucleus is providing an enormous surface area and an enormous internal volume for the gas and the dust production. This is compared to the smaller comets that typically develop prominent tails. They do so during their solar approaches in our solar system. The surface to volume scaling relationships are suggesting that this object, it could be maintaining very high activity levels throughout its perihelion passage. It would not be experiencing a rapid depletion of its volatile materials. Multiple different tail structures might be developing at the same time, as the different chemical species are responding to the solar heating and to the radiation pressure through their own distinct physical mechanisms. The carbon dioxide, the water vapor, and the dust particles of various sizes. And potentially the metallic vapors could all be creating separate tail components with different orientations, colors, and temporal evolution patterns. Ground-based observers in both of the hemispheres might be able to achieve something. They might be able to achieve a naked-eye visibility of the tail system. They could do so during the post-perihelion emergence from the solar conjunction. This would happen in December of 2025. The tail of this comet could potentially become one of the most spectacular astronomical displays that are visible from the Earth. It could be comparable to the historically bright comets that have captured our attention. They have captured our public attention and our cultural significance. Space-based observatories will be able to document the tail development and its evolution with an unprecedented level of detail. They will do so through some coordinated observations across multiple wavelength ranges. Ultraviolet imaging will be able to reveal the gas compositions and the ionization states, while the infrared measurements will be able to map the dust temperatures and the size distributions. They will be able to do so throughout the entire structure of the tail. The death throes of this object during its perihelion passage, they might be triggering some explosive fragmentation events that could create multiple tail systems from the separate nucleus fragments. Such breakup events are known to occasionally occur in comets. This happens when the internal pressure from the sublimating gases, when it is able to overcome the gravitational binding forces. This can create some spectacular displays as multiple objects are developing their own independent tails. The observations of this unprecedented display will establish some new protocols for studying the hundreds of additional interstellar visitors that our future surveys are going to be discovering. Advanced survey telescopes are going to be transforming the interstellar object detection. They will be transforming it from a rare accident into a routine discovery, a discovery that will be cataloging hundreds of these cosmic visitors annually. The Vera C. Rubin Observatory will be beginning its full science operations. It will do so in the late part of 2025. It will be revolutionizing the interstellar object detection. It will do so through its systematic sky surveys that are imaging the sky, imaging the entire southern hemisphere every few nights. It will be doing so with an unprecedented sensitivity and automation. This facility alone could be able to discover 6 to 51 additional objects. It could do so over the next decade according to our statistical projections. The 8.4-meter primary mirror of the Rubin Observatory, it is able to collect the light from sky areas that are equivalent to 40 full moons at the same time. This is creating survey capabilities that are dwarfing the previous instruments. Advanced CCD cameras are producing images that are containing over 3 billion pixels. This is requiring the use of machine learning algorithms to process the data and to identify the moving objects against the stellar backgrounds. Automated detection systems that have been developed for the Rubin Observatory. They are using artificial intelligence that has been trained on millions of images, millions of astronomical images, to be able to distinguish the genuine moving objects. to distinguish them from the instrumental artifacts and the cosmic ray hits and the other false positive signals that are in the data. These algorithms are able to achieve detection efficiencies that are exceeding what a human visual inspection can do, while at the same time they are processing data volumes that are impossible to analyze manually by a human being. International coordination among the multiple survey facilities will be creating something. It will be creating global networks that are capable of tracking these objects, tracking the interstellar objects continuously across the entire sky. As the Earth's rotation and its orbital motion are changing our viewing perspectives, the European Space Agency's Euclid mission is one of these, and NASA's Nancy Grace Roman Space Telescope is another. And the ground-based facilities that are all around the world will be contributing. They will be contributing their complementary observations to this effort. Next-generation surveys will be able to detect these objects. They will be able to do so at much greater distances, and they will be able to do so earlier in their solar system passages. This will be providing us with extended observation periods for a detailed characterization before the objects fade. Before they fade beyond our detection limits forever, an earlier detection will be enabling some coordinated observations that will be made by multiple different facilities, and it could potentially be enabling spacecraft missions that are designed to intercept particularly interesting targets. Statistical models have been predicting that the systematic surveys will reveal something. They will reveal the size, distributions, and the compositional diversity, and the population characteristics of the interstellar objects. These are things that remain hidden when the detection depends on chance encounters. Large statistical samples will be enabling some population studies that can distinguish between the different ejection mechanisms and the different source stellar systems of these objects. The discovery rate projections are suggesting that approximately 1 to 2 objects per year, 1 to 2 interstellar objects per year, are achievable with our current technology. This could be increasing to potentially dozens of them annually. This would happen as the detector sensitivity and the survey strategies improve. This transformation from rare events to routine discoveries, it will fundamentally change how the astronomers are approaching this research. Future space missions that are specifically designed for these objects, they could become feasible once the surveys are able to provide sufficient catalogues and they are able to provide sufficient trajectory predictions. The European Space Agency's Comet Interceptor mission is demonstrating something. It is demonstrating a proof of concept for a rapid response spacecraft. A spacecraft that could be able to intercept the newly discovered objects. It could do so during their solar system passages. Advanced spectroscopic capabilities on the future survey telescopes. They will be enabling a chemical characterization of these objects. They will do so during the initial discovery observations. This will be instead of requiring extensive follow-up campaigns. Time domain spectroscopy could be able to reveal the chemical evolution and the activity patterns throughout the entire solar system passages. It could do so with a temporal resolution that is impossible for the individual objects that are studied today. Machine learning applications will be expanding beyond just simple detection. They will be expanding to automated classification systems that can identify the unusual objects that are requiring priority follow-up. The algorithms could be able to flag the potential interstellar visitors. They could do so based on their orbital characteristics and their chemical signatures or their other properties that can distinguish them from the solar system objects. The data processing challenges for the next generation surveys. They will be requiring the developing of new computational architectures, and they will be requiring storage systems that are capable of handling petabyte-scale databases that will have real-time analysis requirements. Cloud computing resources and distributed processing networks will be enabling something. They will be enabling a rapid response to the time-critical discoveries. These routine discoveries will be revealing that the interstellar wanderers, they are representing the most abundant objects in our galaxy. Interstellar objects like 3I divided by Atlas might be representing the most common type of matter in our own Milky Way galaxy. They could be outnumbering all of the stars by ratios that are dwarfing our estimates. Recent theoretical calculations are suggesting that the stellar systems throughout our galaxy are ejecting far more planetary materials, far more of them into the interstellar space than we had previously imagined. This would be creating populations of wandering objects that are exceeding the stellar abundances by factors of millions or billions. 3I divided by Atlas might just be representing a typical member of this vast cosmic diaspora. It might not be an unusual exception at all in the end. Computer simulations of the planetary system formation have shown that the gravitational interactions during the planet assembly, they are naturally ejecting substantial fractions of the available solid materials. They are ejecting them into the interstellar orbits that are between the stars, giant planet migration, and the stellar encounters. And the orbital instabilities are creating the ejection rates that are removing 10 to 90% of the original planetary building materials. They are removing them from their parent stellar systems. The ejection efficiency is known to depend on the stellar system architecture. Systems that are containing multiple giant planets are showing higher ejection rates. They are higher than the simpler configurations that we see. Binary star systems are known to produce even more extreme ejections. They do so through the three-body gravitational interactions. These can be scattering entire planetary systems into the interstellar space. This happens during the close stellar encounters that they have, scaling these high ejection rates across the approximately 400 billion stars. The 400 billion stars that we have in our own galaxy. It produces estimates of the interstellar object populations that are staggering. They are staggering to the imagination of the astronomers. Conservative calculations have suggested that over 10 to the 18th power of individual objects that are larger than 1 kilometer. These are currently wandering between the stars throughout our Milky Way. This is creating number densities that are exceeding the stellar populations, exceeding them by absolutely astronomical margins. The total mass that is contained in these interstellar objects, it might be able to rival the total mass that is in all of the stellar systems. It could do so when you are accounting for the size distributions that are including objects that are ranging from asteroid dimensions to the potential rogue planets that have been ejected intact from their formation. This interstellar matter is representing a previously unrecognized component. A component of the galactic mass budgets that we have. The detection bias is severely limiting our current observational access. Our access to these vast populations of objects. This is because the interstellar objects are appearing bright enough. They are bright enough for discovery only during their brief passages. Through the stellar systems with sufficient illumination. The vast majority of these interstellar wanderers are remaining invisible. They are invisible in the deep darkness that is between the stars. This is creating a kind of a hidden universe of objects that are only occasionally becoming accessible to us. They are doing so through the chance encounters that they have. The chemical diversity that is implied by such enormous populations. It is suggesting that the interstellar objects are carrying samples from virtually every type of stellar system and every type of planetary formation environment throughout our galactic history. Different stellar masses and metallicities and ages and formation epochs, all of these are contributing to the chemical signatures that are spanning the complete range of the cosmic element production and processing mechanisms. Understanding these interstellar object populations will require the developing The developing of new theoretical frameworks for the galactic evolution, frameworks that are accounting for the continuous matter exchange, the exchange that is happening between the stellar systems through ejection and through the occasional capture processes that are occurring. This cosmic recycling network might be playing a crucial role in the distributing of the materials and potentially the biological compounds throughout our galaxy. It would be doing so over the billion-year timescales. The survival statistics for the billion-year interstellar journeys, they are determining what fraction of the ejected materials are remaining structurally intact and chemically recognizable when they are encountering the new stellar systems. Objects like 3I divided by Atlas are demonstrating that substantial preservation is possible. This is suggesting that the ancient materials are circulating throughout our entire galaxy as cosmic time capsules. Radio astronomy searches for the interstellar objects. They are using the thermal emission detection to do this. They could potentially be able to catalogue the populations that are invisible to our optical surveys by detecting the objects in the cold darkness that is between the stars. Such surveys would be requiring an unprecedented sensitivity, and they would require survey strategies that are adapted to the unique observational challenges of detecting the faint thermal sources. The implications of all of this are transforming our understanding of how the chemical elements and potentially life itself, how these things might be spreading throughout the entire cosmos. 3I divided by Atlas is proving that our own solar system is representing something. It is representing a chemical anomaly in our galaxy, a galaxy where most of the planetary formation is following completely different rules. The extreme chemical signatures that have been observed in this object, they are indicating that the water-rich and the carbon-poor planetary systems like our own are occurring very rarely throughout our galactic history. While the carbon dioxide-dominated environments might be representing something, they might be representing the typical conditions for the planetary formation that is happening around most of the stellar types. This revelation is inverting our fundamental assumptions, our assumptions about the nature of cosmic chemistry and about the prevalence of the Earth-like worlds in our universe. The stellar nucleosynthesis processes that have been operating throughout the 13.8 billion-year history of our universe, they have created some systematic variations in the elemental abundances, variations that are depending on the stellar mass and the formation epoch, and the galactic environment that they are in. Stars that have formed during different periods of time. They have produced planets with chemical inventories that are spanning ranges that are far exceeding the narrow conditions that are characterizing our own local solar neighborhood and its planets. The metallicity differences that are between the thick disk and the thin disk, they are demonstrating that the planetary formation chemistry has evolved. It has evolved dramatically as the galaxy has aged, and as the successive generations of stars have enriched the interstellar space, enriched it with all of the different heavy elements. 3I divided by Atlas is carrying the chemical signatures from the epochs when the stellar nucleosynthesis was operating under different conditions that are absent in the present-day galactic environments. Laboratory analysis of the meteorites from our own solar system, it has revealed the isotopic ratios and the elemental abundances that are clustering within some very narrow ranges. This is compared to the diversity that is implied by the galactic chemical evolution models. Our own planetary system has apparently formed from unusually homogeneous materials. This is compared to the chemical chaos that is characterizing most stellar formation. The carbon dioxide to water ratio of 8:1 that has been measured, it might be representing the typical volatile inventories for the planetary systems that have been formed around stars with different masses and with different ages or with different chemical compositions than Our own Sunday, such environments could be producing terrestrial planets, planets with atmospheric chemistry that is fundamentally different from the Earth's own nitrogen and oxygen atmosphere. The habitability assessments for the exoplanets are typically assuming something. They are assuming a water-based biochemistry that is operating under certain conditions, chemical conditions that are similar to our own Earth's environment. 3I divided by Atlas is suggesting that alternative biochemistries are possible, biochemistries that are based on carbon dioxide or methane, or on other chemical foundations might be dominating throughout our galaxy. This would be expanding the potential range of the biological processes. It would be expanding it beyond just our Earth-based analogies. The preservation of the exotic chemistry in this object, it has been preserved over the billion-year timescales. This is demonstrating that the alternative chemical architectures are remaining stable. They are remaining stable under the space environmental conditions. This is suggesting that the unusual planetary chemistry could be persisting. It could be persisting throughout the geological and the astronomical time periods. Such stability is expanding the potential for discovering the chemical signatures. The chemical signatures of the alternative biochemistry in the exoplanet atmospheres. Future astronomical surveys of the exoplanet atmospheres. They will be using the next generation space telescopes. They might be able to reveal that the Earth-like chemical compositions, they are representing some rare exceptions rather than the typical examples. The James Webb Space Telescope and the subsequent facilities, they could be able to detect the atmospheric signatures that are consistent with the carbon dioxide-dominated chemistry that has been observed, understanding the true diversity of the planetary chemistry. It will require us to move beyond our solar system experience. It will require us to embrace the full range of the chemical possibilities that have been demonstrated by the interstellar visitors like this one 3I divided by Atlas, for example. These objects are providing us with direct access to the materials that were formed under conditions that are impossible to study through our solar system samples alone. The implications of all of this are extending to the field of astrobiology, and they are extending to our search for life throughout the entire cosmos. If most of the planetary systems are developing chemical architectures that are different from the Earth's own environment, then the biological processes might be following some pathways that are unknown to our own terrestrial biology. They could be operating through some chemical mechanisms that are adapted to the carbon dioxide-rich atmospheres and the exotic volatile inventories. 3I divided by Atlas is representing more than just an unusual interstellar visitor. This ancient wanderer is carrying some revolutionary evidence that our understanding of the cosmic chemistry is incomplete, and our understanding of the planetary formation is also incomplete, and the potential for life throughout the universe is also incomplete. All of this is requiring a fundamental revision of our ideas, a revision that is based on a chemical diversity that is far exceeding our previous imagination of what is possible. The successful detection and characterization of this object and the scientific analysis of it is establishing our capability to be able to intercept and study these fleeting cosmic messengers. This is opening up some unprecedented opportunities for exploring the chemical evolution of our own galaxy through the direct observation of the materials that were formed under different conditions that are spanning billions of years of cosmic history. As 3I divided by Atlas is continuing its eternal journey into the darkness that is beyond our own solar system, it is leaving behind a transformed scientific understanding, and it is establishing some new paradigms for studying the vast population of the interstellar wanderers that are carrying the chemical heritage of our own galaxy through the cosmic void.